Good morning, everybody. Let us start with module number 3, which is extension of instrument ranges. Coming to the syllabus, we have shunts and multipliers, construction and theory of instrument transformers, equations for ratio and phase angle errors of CT and PT, turns compensation, illustrative examples, Silby's method of testing CT, and desirable features of ammeters and voltmeters. So coming to the introduction part of module 3, this is first part of module 3 where we'll be seeing measurement of current and voltage. So in this chapter you'll be seeing measurement of current and voltage of low value and high value. Whenever you want to measure low voltage and currents, you can preferably use ammeters and voltmeters. Whenever the power levels are high, we'll be using CT and PT, current transformer and potential transformers, typically called as instrument transformers. So before going into the details, let us first see the basics. What are the essential characteristics of a measuring instrument? Generally, any measuring instrument must not alter the circuit conditions. May it be a voltmeter or ammeter or any such instrument, whenever you are going to use that instrument as a measuring device in your circuit, it must not alter the existing circuit conditions. Second condition is the measuring instrument must always consume low power as possible. Ideally, it should not consume any power, but practically it will consume some power. So we should see to that it should be designed in such a way that it will consume as low power as possible. So these are the essential characteristic of any measuring instrument. Next, we see an instrument called as PMMC instrument, permanent magnet moving coil instrument. This PMMC instrument basically is going to behave as both ammeter or voltmeter. So the same instrument can be used as both ammeter as well as voltmeter depending upon the way the terminals are connected in the circuit. It either behaves as an ammeter or a voltmeter. So this PMMC instrument basically works on d'Arsonval's principle, which says whenever a current carrying conductor is placed in a magnetic field, it experiences a force. So now let us see how to use this PMMC instrument as a voltmeter and ammeter. So here we have the schematic of PMMC instrument. We are having a permanent magnet marked by north pole and south pole on either sides. In between you are having a a small core. On that core a coil is being wound, and on the same core we are having a pointer attached. That pointer basically reads on the scale, and the terminals of the coils 1 and 2 have been brought out for connectivity. So this is PMMC, basic PMMC instrument. So now in case we connect these terminals 1 and 2 in series with the test circuit, then the current that is flowing through this particular coil will be proportional to the current flowing in the circuit, the load current flowing in the circuit. Hence, as per d'Arsonval principle, any current carrying conductor placed in the influence of magnetic field experiences a force. So it experiences a force and it observes a torque, and the pointer is going to deflect to indicate the reading. So here we can understand that the torque experience depends upon the current flowing through this coil, and the current that is flowing through this coil, since it is connected in series with the test circuit, it is nothing but the load current. So this instrument hence behaves as an ammeter and measures the current flowing in the circuit. On the other hand, whenever the terminals 1 and 2 are connected across a component in the test circuit, that is in parallel to a component in the test circuit, whenever it is connected, the coil of the meter carries current proportional to the potential difference across that component. So potential difference across that particular component drives the current through this PMMC coil. Hence the coil and the pointer experiences a torque. So the torque experienced by this particular coil depends on current flowing through the coil, and that current flowing depends upon the potential difference observed or experienced across the component of the test circuit. Hence, this will measure the potential difference, and hence it behaves as a voltmeter, and it is going to measure the unknown voltage across the component. So the same instrument, whether you connect it in series with the test circuit or across a component, decides whether it should behave as an ammeter or it should behave as a voltmeter. Now, next we'll talk about shunts and multipliers. So coming to the shunts and multipliers, in order to extend the range of this basic PMMC instrument, we'll be using shunts and multipliers, because this basic PMMC instrument range of current or voltage it is going to measure is very less. So to extend the range, we go for shunts and multipliers. So first we'll talk about shunts. So basic PMMC instrument, as you can see, can measure only up to 100 milliamperes. So to extend the range, we'll be using a resistance in parallel to this basic meter. As you can see in the diagram here, a resistance is connected in parallel to the basic meter. So whenever a resistance is connected in parallel to this basic meter, the range of this meter is said to be extended, because here test current I is flowing into the circuit. As per KCL, it is getting divided at this junction. Part of the current is flowing through R shunt, which is nothing but I shunt. Remaining part is flowing through the basic meter, which is IM, meter current IM, and the basic meter has got its own resistance RM. So now the actual current that the entire instrument can measure is I shunt plus IM, which is nothing but I. Otherwise, if the shunt wouldn't be there, the current that this meter could measure was just IM, which was 100, only up to 100 milliamperes. Now, since we have connected a shunt here, this instrument as a whole is a combination of R shunt and basic meter, which can measure I shunt plus IM. So the range has been extended. So since you are connecting it in parallel, this resistance is called as shunt. Now we are going to select the coming to the selection of this R shunt. The selection is done in such a way that only the rated current flows through the basic meter, that is up to 100 milliamperes. Remaining current will be bypassed through this particular shunt. Now coming to the design of shunt. Design of shunt in the sense how to calculate the value of R shunt. So from this circuit you can see R shunt and basic meter are connected in parallel. So voltage happens to be same in parallel. So voltage across the shunt is I shunt R shunt. Voltage across the basic meter is IM into RM. That being the case, I shunt R shunt will be equal to IM into RM. From this we can write down the expression for R shunt, which is equal to IM RM divided by I shunt. And this I shunt can also be expressed in terms of main current, which is I minus IM because of KCL. So this can be finally written as R shunt equal to IM RM divided by I minus IM, where I shunt is current flowing through shunt, RM is basic meter resistance, IM is current through basic meter, capital A is current to be measured, R shunt is shunt resistance. So this is how you are going to design the shunt. Now let us just see a small illustrative example. A 1 milliampere meter D'Arson wall movement with an internal resistance of 100 ohm is to be converted into 0 to 100 milliampere ammeter. Calculate the shunt required. So the basic meter can read 1 milliampere. It should be converted into an instrument that can read up to 100 milliamperes. So this in this problem, we have an instrument, PMMC instrument, which can read only 1 milliampere. We should extend its range to 100 milliampere. And internal resistance of the basic meter is given as 100 ohms. So just now we have seen the design of shunt. So R shunt is given by IM by I minus IM. IM is nothing but the meter current, that is 1 milliampere, 1 into 10 power minus 3. RM is given as 100, that is 100. Then capital I is the required current, that is 100 into 10 power minus 3, and IM is 1 into 10 power minus 3. If you simplify this, you'll be getting, if you calculate this, you'll be getting 1.01 ohm. So in order to extend the range from 1 milliampere to 100 milliampere, Shunt resistance required is 1.01 ohms. And here, for your additional reference, you can just have a look at this, how the measurement of test current is done using ammeter. That is, whenever a test current I, unknown current I, is just blindly passed through the instrument, how the measurement is being done. That's what this says. So here, the shunt resistance basically is 1.35 ohm in this instrument. Basic meter 0 to 2 milliamperes. Assume that you are going to just pass some test current I through this meter, and that I has to be measured. This is what happens whenever you are given with an instrument of some range. Say the range here is 0 to 150 milliamperes. You are going to connect this ammeter in some test circuit, and you want to measure the current flowing in that. That is nothing but your capital I. So if you have to measure that, the basic meter range is 0 to 2 milliamperes. Range of the instrument is 150 milliamperes. So whenever you are going to connect this, current flows through it. It shows some deflection. That deflection is nothing but Im. Let us assume it will show 1 milliampere, for example. Then I know the value of Rm, which is fixed here, which is 100. Rm is basically fixed. So I shunt will be equal to Im Rm by R shunt. We know R shunt and Rm, and we have seen the deflection Im. So 1 into 10 power minus 3 into 100 divided by 1.35 will give me I shunt, which is 74 milliamperes. So I have got the value of I shunt calculated now. So this I shunt, when you add it with Im, will give you the unknown current. So Im is 1 milliampere. Add it with the 74 milliampere, will be getting 75 milliampere. So you can come to a conclusion that the actual current flowing through this test circuit is 75 milliampere, as you can see over here. Then sometimes shunts aren't good enough. You need uh, higher range ammeters. So in order to extend the range further, we'll go for multi-range ammeters. So if you need multi-range ammeters, you will be connecting several shunts in parallel, as you can see in the circuit diagram. You have R1, R2, R3, R4, and we employ a switch here, which is called as make before break. Make before break, in the sense you will never leave the open circuited condition during the operation of the switch. That is, during the transition, we'll see to that the switching operation will not happen at open circuit. So that is called as make before break switch. So required range, we'll be connecting it to R1, R2, R3, R4. For one particular range, I'll connect it to R4. For higher range, I may connect it to R3, R2, R1, and so on. And coming to the design, same formula, R shunt is equal to Im Rm by I minus Im. If you just simplify this mathematically, you can just divide the denominator by Im, so that you have numerator and denominator, if you divide by Im, you have Rm divided by I by Im minus 1. If you call I by Im as small m, you have Rm by m minus 1. So if you try to write the expression for R1, R2, R3, R4, R1 is Rm by M1 minus 1, where M1 is I1 by Im. Similarly, R2, R3, and R4. This is called as the design of multi-range ammeters. We have some drawbacks of multi-range ammeters. That is, if you have to use multi-range ammeter, many shunts will be required. It becomes expensive, and even your make before break switch is also quite expensive. So in order to avoid this, we go for design of universal shunt or Ayrton shunt. It's called as Ayrton shunts. So this is the arrangement where you are having R1, R2, R3 connected as shown over here, and you have the basic ammeter. The total shunt is connected across the basic meter. And here also we are having a switch which takes different positions 1, 2, and 3. Whenever the switch is connected to position number 1, you can see to that R1 will act as shunt whenever it is connected to this position. Whenever it is connected to position 1, only R1 will remain in the circuit. Whenever it is connected to position number 2, R2 will be there in the circuit, and R1, R2 will be there in the circuit, and whenever it is connected to position number 3, R1, R2, R3 will be there in the circuit. So let us see the expressions. When switch is at position number 1, R1 will behave as shunt. So if you equate for the voltage drop on both the sides, you can see that R1 will act as a shunt, your R2, R3 will act in series with your RM. So if you try to equate for the potential drop, I1 R1 will be equal to R2 plus R3 plus RM multiplied by IM. So this we'll call it as equation number 1. Next, whenever the switch is in position number 2, combination of R1 and R2 will act as shunt. So the equation will be I2 into R1 plus R2 will be equal to R3 plus RM into IM. Whenever the switch is in position number 3, all the three resistances combination will act as shunt. So you have R1 plus R2 plus R3 into I3 will be equal to IM into RM. So if we solve these three equations, we have three equations and three unknowns, you will be able to calculate the required values of R1, R2 and R3 from this expressions. So this finishes with design of ammeter, multi-range ammeter, universal shunt or Ariton shunt. In the next session, we'll be continuing with basic voltmeter, multi-range voltmeter.